Namaste, and welcome back to JEE Physics with Typical Monk. This is Class 15, Electrostatics. The first part, the field and Gauss's law. Every charge reaches out into the space around it and fills it with a field, an invisible push, waiting for any other charge to arrive. Coulomb told us the force between two charges. The field tells us what one charge does to all of space. And a single beautiful law, Gauss's lead symmetry, hand us the field of a sheet, a wire, or a sphere in one line, one idea at a time. Here is what you will learn today. First, Coulomb's law and the electric field. Second, field lines and the field of a dipole. Third, electric flux and Gauss's law. Fourth, fields found by Gauss, the sheet, the wire, the sphere, and the shell. And fifth, a dipole in a uniform field plus the drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. Coulomb's law. The force between two charges, F equals kq1q2 over r squared, where k equals 1 over 4 pi epsilon naught. The electric field. The force per unit positive charge, E equals F over q naught, and for a point charge, E equals kq over r squared, pointing away from a positive charge. Electric flux, phi equals E dot A, the field lines passing through a surface. And Gauss's law. The closed surface integral of E dot dA equals the enclosed charge over epsilon naught. Now look at the picture. The electric field, drawn as lines, out of a positive charge on the left and into a negative charge on the right. The electric field itself. It is the force per unit positive charge, E equals F over q naught, a vector defined at every point of space. Field lines. They start on positive charges and end on negative ones, and they point exactly the way a positive test charge would move. Density is strength. Where the lines crowd together, the field is strong, and a point charge's field falls off as 1 over r squared. And the dipole. Two equal and opposite charges far away, its field falls off faster, as 1 over r cubed. Now, the working formulas, the ones the exam turns into marks. The ribbon holds the anchors. Coulomb's law, the field and the flux. Coulomb's law, F equals 1 over 4 pi epsilon naught times q1 q2 over r squared, like charges repel, unlike charges attract, and k equals 9 times 10 to the 9. The field of a point charge, E equals kq over r squared, directed radially, away from a positive charge and toward a negative one. The dipole field, on the axis, E equals 2kp over r cubed, on the equator, E equals kp over r cubed. The actual field is twice the equatorial. And superposition. The total field at a point is the vector sum of the fields due to all the individual charges. Let us work the G favorite, the field of a uniformly charged sphere, by Gauss's law. Take a solid sphere of radius r, carrying total charge q. Find the field both inside and outside. The surface first. Take a concentric Gaussian sphere of radius r. By symmetry, the field E is radial and has one single value everywhere on it. Gauss's law. The closed surface integral of E dot d equals E times 4 pi r squared, which equals the enclosed charge over epsilon naught. Outside. For r greater than r, the whole charge q is enclosed. So E equals kq over r squared. The sphere acts exactly like a point charge sitting at its center. Inside. For r less than r, only the charge within, q equals q times r cubed over r cubed, is enclosed. So E equals kqr over r cubed. The field grows linearly with r. The picture. The field is 0 at the center, rises to kq over r squared at the surface, and then falls off as 1 over r squared outside. Now the imaginary surface that does all the work, the Gaussian surface. A Gaussian surface. It is an imaginary closed surface, and we choose its shape to match the symmetry of the charge inside. Electric flux. Phi equals the closed surface integral of E dot d, the number of field lines piercing through the surface. Gauss's law. That flux equals the enclosed charge over epsilon naught. the closed surface integral of E dot d equals q over epsilon naught. And the payoff: for a sphere, a wire, or a sheet, the symmetry makes E constant on the surface, so the field comes straight out in a single line. Now what JEE actually asks: 5 pointers. 1. Coulomb's law. F equals kq1q2 over r squared, with k equals 1 over 4 pi epsilon naught, equal to 9 times 10 to the 9. 2. The field of a point charge, E equals kq over r squared, and for a dipole, axial 2k cup over r cubed, equatorial k cup over r cubed. 3. Flux, phi equals E dot A, and Gauss, the closed surface integral of E dot dA, equals the enclosed charge over epsilon naught. 4. By Gauss, an infinite sheet gives sigma over 2 epsilon naught independent of distance near a conductor, sigma over epsilon naught, a long wire, lambda over 2 pi epsilon naught r. And 5. A dipole in a uniform field. The torque, tau equals p e sine theta, and the potential energy, U equals minus p e cosine theta. Now an assertion and reason drill. For each pair, are both true, and does the reason explain the assertion? First pair. Assertion: the field of an infinite charge sheet is the same at all distances from it. Now reason: by Gauss's law, the flux through a pillbox depends only on the enclosed charge, not on the distance. Both are true, and the reason directly explains the assertion. The answer is A. Second pair. Assertion: electrostatic field lines can form closed loops. Reason: field lines start on positive charges and end on negative charges. The reason is true, but the assertion is false. Electrostatic field lines never form closed loops. They always begin and end on charges. The answer is D. Third pair. Assertion: the total flux through a closed surface depends only on the charge enclosed. Reason: the electric field is a vector quantity. Both are true, but the field being a vector does not explain Gauss's law. The flux depending only on enclosed charge is the law itself. So the reason does not explain the assertion. The answer is B. Now match each quantity to its formula. Coulomb's law goes to kq1 q2 over r squared. The field of a point charge goes to kq over r squared. Gauss's law goes to the enclosed charge over epsilon naught. And the field of an infinite sheet goes to sigma over 2 epsilon naught. 4 pairs, each worth committing to memory. Now, how many of these 3 statements are correct? 1. The field of a point charge falls off as 1 over r squared. That is correct. 2. The field of an infinite charge sheet decreases with distance. That is wrong. The sheet's field, sigma over 2 epsilon naught, is independent of distance. 3. Gauss's law relates the flux through a closed surface to the charge enclosed. That is correct. So the answer: 2 are correct, statements 1 and 3. The trap is statement 2. The infinite sheet's field does not change with distance. Now the 2 mistakes that quietly cost marks. The myth: Gauss's law gives the field only for a spherical surface. The truth: Gauss's law holds for any closed surface at all. It just gives the field easily only when the symmetry makes E constant on the surface. The second myth: the dipole field falls off as 1 over r squared, like a point charge. The truth: the dipole field falls faster as 1 over r cubed, because the 2 opposite charges nearly cancel far away. Now, test yourself. Answer in your head before the reveal. That is how JEE speed is built. Here we go. Question 1. The field of a point charge varies as 1 over r squared. Question 2. A dipole's field far away varies as 1 over r cubed. Question 3. Gauss's law: the total flux equals the enclosed charge over epsilon naught. Question 4. The field of an infinite charged sheet, sigma over 2 epsilon naught. And question 5. The ratio of the axial to the equatorial dipole field, 2:1. Let us gather it all in one breath. Coulomb: F equals kq1 q2 over r squared. The field E equals kq over r squared away from a positive charge. Field lines run from positive to negative, and where they crowd together, the field is strong. The dipole axial 2 kp over r cubed, equatorial kp over r cubed, and the field falls off as 1 over r cubed. Flux phi equals E dot A, and Gauss, the closed surface integral of E dot dA equals q over epsilon naught. The sheet, sigma over 2 epsilon naught, and a charged sphere is a point charge outside, with zero field inside a shell. Next class, electrostatic potential and capacitance. The potential V, the relation E equals minus d by dr, and the capacitor. A charge fills space with a field. Coulomb sets its string, and Gauss's law lets symmetry deliver the field of a sheet, a wire, or a sphere in a single stroke. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack JEE. I will see you in the next class.